Okay, I want to give a little summary of how to use the curve fitting features of Excel to fit curves, specifically the normal curves, to data for production of fossil fuels. And we'll take as an example, a well-known example, and that is the data for the United States oil production. But before we do, I want to look for a moment at the normal distribution curve, and in particular to talk about the two ways that we can interpret that curve. One, which you see on the left, and again, if we're thinking of this in terms of fossil fuel production, this would be, for example, the production of the total amount produced within a particular year, within a year, uh, for a given year. So you see on the x-axis here some numbers, and these can be interpreted as years, and then the vertical height would be the production per year. This is the distribution of production over time, and this is just a fictitious representation, and I want to talk a little bit about how these parameters affect the shape of these curves. On the right is an equivalent, or alternative maybe is the best term, alternative representation of this same information in the left. And what this is really the area under the curve from minus infinity, if you will, all the way up to the current year. So, for example, up to 1950 in this graph on the left, the area under the curve from 0 all the way up to 1950 is approximately 48,000, 46,000 and some odd units there, it looks like. So this is the area under the curve, or the cumulative value. If we add all of this up or integrate all of this up, this is the value at each year. The total amount that has been produced from the beginning of time up until the current time. Okay, what I've put here in the title of these graphs is the name of an Excel function. It's called NormDist, which stands for normal distribution. And if you use the Excel help on this, just to bring it up, and this is probably too tiny to see, but as I type norm.dist, norm distribution, it brings up a little floating help that says NormDist is a function that takes x as a value, mean as a value, standard deviation as a value, and something called cumulative. Well, x is the year, mean is the year of the peak, that is the average value, and standard deviation is a parameter that describes the spread of this curve, how much this curve spread. And what I want to show, those numbers are listed up here in the top part of the screen. In other words, the one that's labeled peak is actually the mean value, and the one that's labeled STDEV, of course, is the standard deviation. So you have peak and you have standard deviation. Excellent. There's one other, this last parameter, cumulative. Well, that's a logical flag, just something that's either true or false. You can just apply the word true or false to this function. But when norm distribution is equal to false, when cumulative is equal to false in norm distribution, then that means it's just going to give the distribution and not the accumulation or cumulative value of that curve. So when cumulative is equal to false, norm dist generates a curve like this. When cumulative is equal to true, the same function, norm distribution, generates this curve over here. There's one other parameter that is involved in both of these plots that's not involved in calling norm distribution, and that is the area under the curve. In other words, the area under the curve for norm distribution is unity, is 1. But if we want to scale that, all we need to do is multiply the value that we get back from norm distribution by this number, the area under the curve. And so in above here you see ultimate is listed as, I put 220 million barrels of oil. So by multiplying ultimate times norm distribution with either cumulative equal false or cumulative equal true, I get these curves over here. So what I want to do is explore, how these change. If I change the mean value in this function call, which is the year of the peak, from 1970 to 2000, for example, that's going to shift the whole curve over. That's all it's going to do. I can make it 1950. It's going to shift the whole curve back. So that's all that does, is a simple shifting back and forth. If I change this standard deviation, that's going to change the shape of this curve. If I make it real small, like 10, it's going to pull everything in at the edges. It's going to pull these values in, but it's also going to shoot that peak up because the area under the curve has to stay the same. So if I make this 10 instead of 25, it changes the scale quite a bit. As you can see in this cumulative, the final value, the ultimate recoverable amount, is this last value where the curve plateaus and levels off, and that doesn't change. But what does change is the time period over which that does occur. So if we keep this back at something like 50 years, then we get kind of a broad curve. And just to show, if I change this, let's make it, instead of 50, let's go back to 25. Because when we have 25, we get a good plateau over here, and we can see that ultimate value. But now, if we change this, instead of 220 million barrels of oil, I make it 150 million barrels of oil. Then you can see that just drops this drops the magnitude down here, drops this magnitude down to 150 million barrels. So where this plateaus on the right, that becomes the ultimate value. Okay, so I just wanted to demonstrate this NormDist function and to talk about how, when we calculate things with that, what we're getting when cumulative equals false and cumulative equals true. Because we want to use this function in this curve fitting exercise that we're going to do. Okay, enough about that. Let's take a look at the data that we have. The data that we have available, I think I've got this somewhere. Nope, that is not it. And I don't think that is either. Well, maybe I don't have that. I thought I had it here for you. I do have it here for you. It's just hidden behind Google. Here we go. So if we look at the United States Information Administration, and for example, if we're just interested in domestic, actually historical, domestic production of oil. Yeah, I did this search before, so it comes up. But historical domestic oil production. That sounds pretty straightforward. But the first link that comes up is at this Energy Information Administration site. And I've tried to get you to believe that that's a reliable site that we can go to find this data. And if we go there, first of all, we'll see a table that comes up that just has the recent history from 2007 up through 2012. But if you look over here, and that's for the total U.S. production. Then it's also broken down by state and by region down here. And if you wanted to know how much they brought out of the ground in South Dakota, for example, there's data on that. But we're interested in the total U.S. production. And if you look off to the right, it says View History, and it says 1859 through 2012. So if we click on that, then we can see a graph that comes up, and it goes way back into the 1800s, but it has the production year over year, and the peak that we've talked about, the Hubbard's peak that occurred right around 1970, 1971, and then we've been downhill since. There have been some slight rises and long downhill, and you can see we're in the middle of a recent upward trend. So it may be interesting to find out how far the technology takes us on the increase in oil production. But regardless, these are the data that we seek, and we would like to get these numbers into a table. If you, let's see, I think if I scroll down below this graph, he has all the data that appears up above in thousands of barrels of oil produced each year. Thousands of barrels of oil. And the numbers start at 2 in 1959, and they go up to 2.374 million barrels of oil in 2012, which is the most recent year. But we want to get these numbers. They have them in this table, and I can cut and paste them from here, but then they're sort of in this tabular version. So I can go instead to something that says download XLS file, and if I roll the dice on that, I think it will bring up an Excel picture. But what I'm going to show you here is it's a little bit disappointing, because now if we go to look at the data that are involved here, now it only goes back to 1900. The other little table went back to 1859 with the 2 barrels of oil they got in 1859. So it might be worthwhile to go back to the site and cut and paste these couple of lines here that get you back up to the 1900s. So I'll try to do that. Copy those, and let's see if I can paste them into here. As I say, they're not in the format that we might like. So let's see if we can make that happen. The easiest thing to do might be to copy this and then paste it with a transpose. So now that at least they're in columns, and now if we can just kind of stack them one behind the other, we might be able to make it happen. So let's do this. 1950s and 1960s. So we think this is 1860 right here, and this is 1859. And then just I apologize, I'll keep working on this. If I put this one under that one, and then put this one under that one, and then put the whole mess under the other one. So it's not too complicated, but okay. So we think that's 1859, 1860, and so forth. So we can copy that down by highlighting that pattern and double clicking, and now we've got that, and we'd like to put that just ahead of these other numbers. So I'm going to need to make some space for it, I'm afraid. So let's do that. I can clear all this out. We're through with that. Insert. Hopefully we got enough room in there now. Yeah, we got a little bit of extra. Alright, so now we've got all of that data in there. So here's what I want to do. I want to take these, let's just start by making a picture. Sure, let's just to make a graph of all this, and insert a chart, and that looks good. Let's just move it to another page. So move that to another page, and there you go. So this is the annual U.S. production going from, well, that's interesting. I don't like those numbers there. Let's see if we can change that, because I think we got something a little whacked out. You see what's going on there? He's plotted those as actual number values instead of the interpretation as years. So here's what I want to do. I want to make this number 1859 and this number 1860. Now those actual numbers, I want to make that number. Yeah, that's a number. And that's a number. So what I want to do is copy that pattern all the way down. There we go. So now hopefully I've got, yeah. So now he's interpreting those as numbers rather than the dates that were there before, that Excel was representing, looked like numbers in the table, but now that they're the actual years on the x-axis here. Okay, so this is the this corresponds, if you think about that norm distribution curve that we just looked at, this is with cumulative equal to false. We can create the cumulative curve by going back to this graph and saying, well, here's the cumulative. And maybe we'll wrap the cells, I don't know. Alignment, wrap text, sure. Make it a little bit bigger. There we go. And we can leave it in those same units. I guess they're getting to be kind of big though, aren't they? Let's take, it's in 1,000 barrels. Another 1,000 would be million barrels, and another 1,000 would be billion barrels. Am I right? So if we take this number divided by 1,000,000 or 1E6, then this is the cumulative in billion barrels. Which is not much, but now if we take that number plus this number divided by 1E6 and copy that formula down, that's going to give us something that looks like the total production in billions of barrels. Maybe we should be a little more conventional. We'll put millions of barrels. I'm sorry. So let's change it back. So million barrels, and we'll divide this by 1,000, and we'll divide this by 1,000. There we go. So now we've got some numbers that go up to 206. So let's make a graph of this plot. So now when we plot the years versus the cumulative production, the production we just added up year over year, then we're going to come up with that cumulative curve. So let's make a plot that looks like this, and now move that to another chart. So move that to another chart, sure. So this is the cumulative production. So what we want to do is we want to find the peak year, the standard deviation, that is the mean. The peak year is going to be the mean value. The standard deviation is just a parameter that adjusts how broad the spread is of that curve. And then the ultimate. Remember, the ultimate is where this logistic curve, this curve is going to level off. So let's see if we can't fit a line to this data. That's our next objective. So how do we do that? What we need to do is create a model over here. So here's our NormDist model. And can I please just copy that over here? That would be nice. Yes. So it should say NormDist. I think it says NortDist. NormDist model. So how will we do that? We need three parameters. We need something that says the ultimate. We need something that says the peak year. And then we need this parameter that's the standard deviation. And we can refer to those by name, if you will. And maybe I'll do something I should have done before and make that just a little bit bigger. But I can add some names for this if I would like by highlighting these labels with their value cells and going up here to the Formula tab. And then in the Formula tab, I can say Create from Selection. And I say, what is it telling me? Create names from selection, names from values in the left column. So the names are in the left column, that's true, and the values will be in the right. So I say OK. So now if I put some numbers like this, 220 million, and I put the peak year as about, oh, suppose I don't know. Suppose I thought it was like 1950, or I thought it was 1980, whatever I thought the peak year was. And the standard deviation, I don't know. Suppose it's 25. Well, what does that have to do with anything? Well, I want to create some model values that are based on that. So remember what I said is we're going to take ultimate times our norm distribution function, and I have to give it the value of x. What's the value of x? That's whatever year it is. I have to give it the value of mean. What is that? The mean value is that peak year, the cell that refers to that peak year. And then standard deviation is whatever number I gave it. Now, what value do I want to use here? Cumulative equals true or cumulative equals false? Well, the truth is I can use either one to fit to either one of those curves, but I'm going to do the cumulative curve because it will be the most revealing, I believe, for us. So let's use cumulative equals to true. We want to get the cumulative value. So I'm going to set that cell equal to ultimate, which is a value that I've set over here, times norm distribution, norm.dist, of A4, the current year. Peak is the mean year, standard the year that the peak would occur, and then standard deviation is that spread. And true means I want the cumulative. So when I do that, and then I copy this all the way down, you can see I just have some arbitrary numbers that I put in there, and you see that they don't match very well. I would like for these to match. And let me maybe illustrate this by taking this column and this column, the model, and putting that on the same axis as this curve. So here's what I want to do is go in here and paste special. Paste space special, and a new series and categories are in the X row, and well, I guess we could leave that off, but I've already done it. So here we go, and bang, there's my. And one thing I want to do is I want to format that line so that I have only a line, and it can be a. Let's leave it a red line, then we'll be able to see it more clearly. And I want to turn those markers off. So markers, no markers. So there we go. So what this means is for the parameters that I gave it, the cumulative curve, the model looks like this. But the actual data looks like that. So the idea is we want to adjust those three parameters that are in that model so that this model matches this data. Now how can we do that? Well, we can do that by trial and error. We can just go in there and change those values and keep looking at the graph to see how it matches up. But we can also do that by minimizing the difference, the error, if you will, the difference between this curve and the corresponding value on this curve. And the way we can and add all those up, we do minimize the distance between these curves. So that's minimizing the sum of the squared errors between these two curves. That's what we want to do. So let's do that. But before we do that, I want to go ahead and extend this curve out, maybe to the year 2100 or so that we can sort of see the full effect when we get done here. So let's go back over here, and I'm just going to increase these years here. I don't know how far you want to go. Gosh, it's 2150. That ought to, maybe that's far enough. And now what we want to do is we want to increase this model, just that we're going to plot this out. So this model we can calculate into the future once we find those parameters. Well, I screwed something up, didn't I? No, I didn't. I've got it spot on. Okay, so we want to find those three values that will minimize the difference between the data values and the model values. So let's make one more column and call that the error or the difference. And just whichever one let's take the cumulative minus the model. There you go. And just do the same thing all the way down. And I'm going to make a name for these the same way I did those others, difference. It just makes it a little bit easier. Formulas, create from selection, top row. There you go. So now the name difference refers to all the values that are in that column. So here's what I want to do. I'm going to call this minimize this. Yeah, there you go. What am I going to minimize? Well, if I take the sum product, that is the dot product of the difference with itself, this will give me the first value times the first value plus the second value times the second value plus the third value times the third value. It's going to take the product of the corresponding entries of these two vectors, difference and itself, difference, and add all those up. Take the products and add them all of them up. And that's the number that I get. It's really a big number. But here's what I want to do. I want Excel to vary these values until this is minimized. And there's a way to do that, and that's what we heard in the lecture today. There's a button in Excel called Solver that will do that. So if I go to the Data tab and I go to Solver, I get a little dialog box that says, what is it that you want to do? You want to set an objective. What objective? Well, this one, the one that I had highlighted, but if not, I just highlight that cell. What do I want to do? I want to set it to a maximum value, a minimum value, or some particular value. But we want to minimize that value. We want to make that error between the model and the data as small as we can. How are we going to do that? What cells do we need to change to do that? Well, I can type in those names I created, or I can just go to the spreadsheet. I do have to spell them correctly if I choose to type them in. Ultimate, peak, and standard deviation. So I'm hoping that those names make sense. If they don't, I can just go in here and highlight those cells. But let's just let that go and see what happens. So boom, he came back and said, hey, that was as good as I could do. Do you want to look at that or not? So yeah, I'm gonna give it a shot. So he changed all these numbers in here, and you can see he changed the peak to 1975 instead of 1970, and came up with a standard deviation and a new ultimate of 226 million instead of the 222 million. So how does it look on the chart? Well, let's see. Oh, my second series, they're perfectly aligned. I just need to make sure that I meant to extend this second graph while I could get to it. Which one is this? That's series. This is series 2. This is it. So I want to go on out to, I don't know what this was, 200? I think it was 200 or something. Maybe it's more. But once I get it out there, I can see. How far did that go? We went actually down to 295. So let me plot that all the way down to 295. Although you can see we don't need that many to get it. 295. Yep. So the curve flattens out, and the ultimate, we're going to reach the ultimate according to this graph. We're going to reach that ultimate before the year 2050, according to this graph, according to this analysis. Okay, so just to review, and then I'll move on. I've been talking about this a long time, but we got the data from the Energy Information Administration, and we came up with the cumulative production data by adding all of those up, adding up all these values that we got for the annual production for each year. So, and we summed all those up. Then we generated a model using the Excel function norm.dist. That's a normal distribution function. And so we had a model. We had 3 parameters that control the shape of that model curve. The ultimate, which is the area under the curve, under the bell curve, or ultimate is also the final value that is achieved when all of the oil has been produced. The peak or mean value, which is the middle of the bell-shaped curve, and then the standard deviation, which is just a parameter that describes the spread of that bell-shaped curve. But we represented that in the cumulative form, or we chose to. We could also do it in the bell curve shaped form. And we made this plot, which is fairly convincing that the data are falling along this this predictive curve. And when we did that, we used Excel to minimize the sum of the differences squared. We took the difference at each year, and then we added all those up, squared them, I'm sorry, and added them all up. And that's what this cell is over here. And then we asked Excel to vary these parameters in the model until this discrepancy, the difference between the curve and the data, is a minimum. Okay, so gone on with this a little bit longer than I intended to. There's a lot of information in here, so thanks for your attention.